Hey guys, welcome to the next video on OpenCV tutorial for beginners using Python. In this video, we will talk about image gradients in OpenCV. So first of all, what is an image gradient? So an image gradient is a directional change in the intensity or the color inside the image. Now the image gradient of an image is one of the fundamental building blocks in image processing. For example, we use image gradients inside the image to find the edges inside an image. Now there are several image gradient methods available in OpenCV, and we are going to see three of them. First is the Laplacian derivatives, second is the Sobel X method, and third one will be the Sobel Y methods. And all these methods which I mentioned are different gradient functions which uses different mathematical operations to produce the required image. So the Laplacian calculates the Laplacian derivatives, whereas Sobel method is joint, Gaussian and differentiation operations. But don't be overwhelmed with the details. You just need to keep in mind that these are just the functions which we use for finding out the gradients of an image to analyze the image. So let's use the first method, which is called the Laplacian gradient. Now to start with, I have this initial code and you might already know what this code is doing. So first of all, I'm just reading this image messy5.jpg in the grayscale mode using the imread method, and then I'm just loading this image using the matplotlib window. So let's first see how the result looks like. So this is going to look like this. This is just a normal image of Messy, and let's see how we can apply the Laplacian method to find out the Laplacian gradient of an image. So for that, we are going to declare a variable called lap, and then there is a function available inside your CV2 library which is called Laplacian, and this Laplacian method takes few arguments. First argument is the image. The second argument here will be the data type which we are going to use, which is called cv2.cv_64f. So cv2.cv_64f is just a data type, and we are using a 64-bit float due to the negative slope induced by transforming the image from white to black. So you just need to keep in mind that this is just a data type which is 64-bit float, and it supports the negative numbers which we will be dealing with when the Laplacian method is run on our image. Now in the next line, what we are going to do is we are going to take the absolute value of our Laplacian image transformation, and we are going to convert this value back to the unsigned 8-bit integer which is suitable for our output. So I'm going to just write lap, and then using the numpy uint method, so np.uint8, and as an argument we are going to pass np.absolute, and then inside the absolute method we are going to just pass our image, which is going to give us the absolute value of our Laplacian image transformation, which is going to convert this into the unsigned 8-bit integer. Now let's see the result of this Laplacian gradient. So I'm going to just add a new title to my title array which is called Laplacian, and also inside the images list I'm going to add this lap variable which contains this image right after the Laplacian gradient is applied here. And here the range will be 2, and we are going to see it in 1:2 format on the matplotlib window. So here you can see the original image, which is this one, and after the Laplacian gradient method is applied on this image, you can see all the edges which are detected by this method when we applied this method on this messy5.jpg image. And an image gradient, as I said, is the directional change in the intensity or the color in an image. So let's close this window, and there is one more argument you can provide here, which is the kernel size. So you can just say k size is equal to 5. This is the kernel size, and I'm going to just run this program once again, and you can see the kernel size is increased, but our result is deteriorated, right? So let's reduce it to 3, and then once again run this program, and the result looks fine. And if you apply k size is equal to 1, let's see the result, and you can see you get the better result, I think. So for now I'm going to just use k size is equal to 3, and now let's use the other two image gradient methods, which are Sobel X and Sobel Y. So these methods, which are called Sobel X and Sobel Y, are also called Sobel gradient representation. So let's just use them, and then we will discuss how they are useful. So first of all, I'm going to declare a variable called Sobel X, and then I'm going to use the method inside this CV2 library, which is called Sobel. So this is the method which takes again few arguments. First is the image, second is again this data type, which is cv2.cv_64, and the third argument here will be the dx. So when you write 1 here, this value can be 1 or 0. So when you write 1 here, that means we want to use the Sobel X method, okay? And then the fourth argument here is the dy value, okay? So this is dx, which is for the x direction, and this is for the dy, which is for the y direction, and dx stands for the order of derivative x, and the dy stands for order of derivative y. Now once again we are going to declare the Sobel y variable. So let's declare the Sobel y, and then cv2.Sobel, and this also takes a few arguments. Here the difference will be only the third and fourth argument, so I'm going to just use the second argument same. The third argument will be 0 for Sobel y, and the fourth argument will be 1, right? So this is the order of derivative x. If it's 1, this is called the order of derivative, which is in the x direction, and in the second case it is in the y direction. And the fifth argument here can be the k size, as we have seen in the Laplacian method. So if you want, you can provide the kernel size also here as the fifth argument, but we are going to skip it for now. Now again we are going to convert these values into the unsigned int, as we have done in the case of Laplacian. So what we are going to do is we are going to once again overwrite this variable Sobel X, and then we are going to use np.uint8, and in the parenthesis we are going to just write np.absolute, and then we are going to just pass the value inside the Sobel X variable. Same we are going to do with the Sobel Y variable, And now let's see the result, how the result looks like. So I'm going to just add these elements inside the title and the image list. So let's add Sobel X and Sobel Y here and here also. So Sobel Y, and now let's increase the range to 4 and let's see it in the form of 2 by 2 matrix on the matplotlib window. So I'm going to just run this code and you can see the result here. So original image, Laplacian gradient, and then Sobel X and Sobel Y. So you can see when you apply the Sobel X gradient method, the direction or the change in direction in the intensity is in the X direction. And when you apply the Sobel Y method, the change in direction in the intensity is in the Y direction. So this is like horizontal and this is in the vertical direction. I have one more image which will illustrate this Sobel X and Sobel Y gradient method in a better way, I think, and this is called Sudoku. So I'm going to just write sudoku.png file, and hopefully I didn't do any mistake in the naming. Yes, it works. So you can see the Laplacian result here, and then Sobel X and Sobel Y result here. So in the Sobel X you can see more vertical lines, so because Sobel Y is good for the directional change in the vertical direction, so you can see more change in intensity in the vertical direction, and using the Sobel Y you can see the directional change in the intensity in the horizontal direction or the Y axis. You can also combine the result of Sobel X and Sobel Y images, and how we can do this, let's see. So to combine these two result, I'm going to just create one more method which is called Sobel combined is equal to cv2 dot, we are going to use the bitwise OR operator in order to merge these two images. So we are going to just write bitwise OR, and then we are going to provide the two sources. One is Sobel X and the other is the Sobel Y image. So this is going to give us the bitwise OR result of these two images, and then we are going to just add this into the title list. So let's say Sobel combined, and also in the image list, so like this, and let's just increase the range to 5 and let's see it in the form of 2 by 3 on matplotlib. So I'm going to just run this once again, and you can see the result now. So this here is the combination of Sobel X and Sobel Y method, and you can see now, you can see the directional change in the vertical as well as in the horizontal direction, because this is the combination of Sobel Y and Sobel X images. So this is how you can use the image gradients inside OpenCV. In the next video we are going to see how we can use Kenny edge detection method to find out the edges in an image. So stay tuned and please rate, comment and subscribe, and I will see you in the next video.